Good morning.
Did y'all get your test back yet?
Yeah, I got mine.
I still haven't gotten mine. I don't know what's going on.
Okay, so good morning. Can you hear me?
Yeah, we can hear you.
Okay, good. All right, so let me first tell you the distribution of the second exam, and the grades are fine. The score distribution. So the highest grade is 95, and then you have 90, 390s. And then next you have 485. And then you have 80. We have 280. And then we have a 75. We have a 70. Okay, so according to the syllabus, so this part would be A, and here would be B and C, okay? All right, so so one of the things about the proof is that for, I think that's the second problem or the third. So we do have a common mistake, although essentially it doesn't influence the proof of the problem, but you still have to pay attention. So that is, you remember, we want you to prove for any real number A, there exists an n such that A is less than 10 to the nth power. And when you use the Archimedean principle, you get A less than n, okay? The Archimedean principle would give you A less than n. And then you want to prove n is less than 10 to the n. So when you use mathematical induction, the inductive step, many people write n to the n0 plus 1. This is equal to 10 to the n0 plus 10 to the n0. So, okay, so this is wrong, okay? So you should understand what is this, 10 to the n0 plus 1. This is equal to 10 to the n0 times 10, okay? It's not times 2. So this is 10 to the n0 plus 9 times 10 to the n0. As I said, the proof works for this, but actually this is larger, okay? This is even larger. All right, just have to be a little bit careful. So for the other problems, I think we had these similar problems given in class. So you can check your notes for the solutions. So I'm not going to talk about the solutions for the exam. It's essentially in your notes. Okay. So today we are going to start a new topic. So this is about elementary Lemma theory. So for Lemma theory, the first thing we need to talk about is the definition of divisor, or number divides another number. Okay, so here's the definition.
Hey, I have a quick question.
Yeah.
Did you finish grading all the tests?
Yes. So did you? Yeah, so Alexander, but I didn't get your exam, right?
No, I emailed it to you.
You emailed to me?
Yeah, I even looked. I sent you pictures. I had it, the date, and I had it in my, I just looked.
It's kind of strange, but I didn't see your exam. Are you, so can you forward, because if you send the exam, it should be in your sent folder. Can you forward it to me?
Yeah, I can do that. Yeah, okay, sorry about it. I don't know what happened, but I definitely sent it. I didn't like leave it blank.
So you should notice that I really need you to forward the file in your sent folder, because I need the time. Okay,
Right.
You understand? Okay, so you forward it to me. So if you send it, I don't know why I didn't see it.
Okay, cool. All right, thank you.
Okay. All right. So the definition is that. So we are talking about, of course, integers. So we first let d and m be integers. The number the number d divides n if there exists an integer k, so that n is equal to d times k. So in this case, we say d is a divisor of n, and n is a multiple of d. So we write d divides n. Okay, so the notion the notation, I would say notation, d does not divide n means that d does not divide n. Okay, so there are some simple properties for divisors. So this is the theorem. So divisibility properties. So the first one is any integer, except the 0 divides 0. When, of course, d is not equal to 0. All right. So when we talk about divisor, we don't talk about 0. Okay. And 0 divides n would imply, well, this is a so here there is a in our notation there's a special case that is 0 divides n, because by this definition, if 0 divides n, which means n is equal to d times 0 times k. In other words, this implies n equal to 0. But this is not commonly used. Okay, so the property here would imply n equal to 0. Okay, so this is only a special case. We call 0 a divisor of 0, but actually 0 is not, in general, is not considered as a divisor. Okay, number 3 is the reflexivity property. So that is n divides n. So this is reflexivity. Okay, so number 4 is that if n divides 1, then this implies n equals to 1 or n equals to -1. So in other words, the special number 1 has only 2 divisors, that is 1 or -1. 1 has only 2 divisors, 1 and -1. Okay, I want to say one thing, Alexander. I received your forward email. Okay, so you
awesome.
get your grade today. Okay.
Do you see the timestamp on it?
Yeah, I see the time. Yeah.
Okay, cool. Thank you.
Okay, and so the 5th property is the transitivity. So if D divides M and N divides M, this would imply D divides N. Okay, this is transitivity. Okay, transitivity. So number 6 is the multiplication property. That is D divides M would imply A times D divides A times N. So this is called the multiplication property. So if you multiply and the original number, you still keep the divisibility. And the next is the cancellation property. That is AD divides AN. This would imply okay, so the cancellation property, of course, requires that A is not equal to 0, and A is not equal to 0. Then this implies D divides N. So this is the cancellation property. So number 8 is a linearity. Linearity means if D divides N and D divides M. So if D divides two numbers N and M, then this implies D divides its linear combination. That is D divides AN plus BN. So this is called so you have a linear combination of N and M. This is called linearity. Property. Okay, number 9 is the comparison property. So if, okay, D and M are positive, and D divides N, then D would be less than or equal to N. Okay, so you should remember these are for positive integers, okay? If D divides N, then D is less than or equal to N. So this is called the comparison property. Okay, so the first few properties are simple. Let me just prove the last two properties, the linearity and the comparison property. Okay, let's look at the proof of number 8. So if D divides N and D divides M, so by definition, we have N is equal to D times P, and M is equal to D times Q. Okay, definition. And now what about AN plus BM? So AN plus BM is equal to A times, we replace M by DQ plus M by N is dP, and B is dQ. So this is equal to a P times D plus BQ times D. And then this is equal to AP plus BQ times D. So this number AN plus BM is equal to AP plus BQ times D, and D divides AM plus BM. By definition. By definition. All right. Next, we prove the number 9, the comparison property. That is for positive integers, if D divides N, then D is less than or equal to N. So proof of 9. So let this the hypothesis. So let D and M be greater than or equal to 0, and D divides N. Then by definition, then we have N is equal to B times Q. Okay, now since D, oh, not B, D. Since D and N are greater than or equal to 0, so we know that Q has to be greater than or equal to 0. Now, since Q is an integer, so we have Q would be greater than or equal to 1. So dq would be greater than or equal to d times 1, because q is greater than or equal to 1, which is equal to d. Therefore, okay, dq is just n. Therefore, n is greater than or equal to d. Okay, comparison property. Okay, look at here. I'm saying since q is greater than or equal to 1, so d times q is greater than or equal to d times 1, right? Okay, but d times 1 is of course equal to d. D times 1 is d. So that's why d times q is greater than or equal to d, right? But you should realize d times q is equal to n. Okay, let me write one more step, then you probably is clearer. So therefore, d times q is greater than or equal to d, right? So you see here, d times q is greater than or equal to d times 1, which is d. So d times q is greater than or equal to d. But d times q is equal to n. So n is greater than or equal to d. All right. Okay, using the language of divisibility, we know that an integer is even if two is a divisor. And it is odd if it is not divisible by 2. Okay, now let's look at another lemma. So I'm going to write in the next page. So for the issue, so the lemma says that if d divides a, then the negative d divides a, and d divides negative n. So the second property is if d divides a, then d divides the absolute value of a. And 3, so the greatest, the largest positive integer that divides a is just absolute value of a, is Okay, so let's look at the proof. So the first one for the lemma just says if you have D as a divisor of A, then negative D is also a divisor of A. On the other hand, if D is a divisor of A, then D is also a divisor of negative A. So you can put signs in front of divisors or in front of the original number, so the divisibility still keeps. So for 1, so if D divides A, by definition, then we know that A is equal to D times K. So we have A is also equal to negative D times negative K. Because you put the two negative signs, so this is still going to be equal to dk, which is A. So by definition, negative D divides A. And on the other hand, negative A would be, by this condition, is negative D times K. So it's equal to D times negative K. So this tells you, hence, D divides negative A. All right, this is 1. So 2, so if D divides A, then we know that there are 3 cases for the absolute value of A. Okay, so then still we can write A is equal to D times K. Now, when you talk about the absolute value of A, and if A is greater than or equal to 0, then absolute value of A is equal to A. So absolute value of A is equal to A, which is equal to D times K. Hence, D divides absolute value of A. On the other hand, if A is less than 0, then absolute value of A is equal to negative A. So we have absolute value of A is equal to negative A is equal to negative D times K. So which is equal to D times negative K. Hence, again, by definition, D divides absolute value of A. So in both cases, A greater than or equal to 0 or A less than 0, you always get D divides the absolute value of A. Therefore, D divides the absolute value of A. Okay. So the third property, the largest positive integer that divides A is the absolute value of A. Okay, so number 3. So if D divides A, because then we want to show D is always less than or equal to absolute value of A. Then, okay, by 2, D divides the absolute value of A. Okay, this is by 2. Now, by 1, since D divides the absolute value of A, then negative D by 1 negative D also divides the absolute value of A. Okay, so remember the comparison property we just proved. If D divides, if you have positive numbers D and A, so let's go back to the comparison property. Number 9. So if Dn are positive and D divides N, then D less than or equal to N. Okay, so in this situation, no matter D is positive or negative, so we always have, so by the comparison property, D would be less than or equal to absolute value of A. Okay, so this tells you any divisor of A is always less than or equal to the absolute value of A. So what's remaining is to show the absolute value of A is a divisor of A. So in other words, we want to show the absolute value of A divides A. Okay. Now we know that absolute value of A by reflexivity divides absolute value of A. So by 1, absolute value of A divides absolute value of A implies absolute value of A divides negative absolute value of A. So this tells you if A is greater than or equal to 0, then absolute value of A is a divisor of A. And if also if A is less than 0, then the absolute value of A is negative A. So absolute value of A is still a divisor of A. Okay. So absolute value of A is a divisor of A. Okay, so once we show these two things, we can claim absolute value of A is the largest positive divisor of A. Okay, so well done. So essentially, this lemma just essentially tells you that when you talk about divisibility, you can put signs freely in front of the divisor or the original number. The divisibility doesn't change. And of course, for any integer, the largest positive divisor is just the absolute value of this integer. And because of this lemma, so for the remaining of our discussions about number theory, we restrict ourselves to just positive integers, because for the negative counterpart is similar, because you are free to put negative signs in front of the numbers. So we only restrict ourselves to positive integers. Okay, so another important subset of integers are called the prime numbers. So prime numbers, what are prime numbers? So first, you should remember the prime number is always greater than or equal to 2. So an integer p greater than or equal to 2 is called prime, a prime number. If the only positive divisors of P is R. One and P. So in other words, a prime numbers has only two positive divisors. That is one. One because one divides all the integers greater than or equal to 2. And for this P is obviously divisor of P itself. So prime numbers are only those numbers with 1 P as its divisors. So an integer greater than or equal to 2 is which is not prime is called composite. Okay, so the first lemma tells us that an integer n greater than or equal to 2 is composite if and only if there exist integers a and b such that n is the product of a and b. A strictly greater than 1, less than n, and b is also strictly between 1 and n. So in other words, a composite number is just a number which can be written as a product of two numbers. These two numbers are strictly between 1 and n. Okay, let's look at the proof. So one direction is clear. So this direction. So this direction means if there exist A and B such that so if there exists AB such that n equals to A times B and A between 1 and n and B between 1 and n, then it's clear A divides n by definition, and A is not equal to 1, A is not equal to n. So this tells you n must be a composite, so n is composite. Okay, because a prime number has only 1 P as it's the set of all divisors, but you have a new divisor which is different from 1 and n. So n is composite. So the important thing is to prove the other direction. Suppose n is composite, then we suppose n is composite. Suppose n is composite, then by definition, n must has a divisor different from 1 and n. Then there exists a positive divisor d of n, so that d is not equal to 1 and d is not equal to n. All right, so since d is a positive divisor, since d is positive, so we have d is greater than or equal to 1. And by the comparison property, since both d and n are positive, so by the comparison property, so we know that d is less than or equal to n. Hence, you have the range d is greater than or equal to 1, less than or equal to n. All right, so maybe I just change the notation d to a, because in the statement of the lemma, we talk about a and b. So let's just change all the d to a, okay? Okay, but since a is not equal to 1 and a is not equal to n, so we get a is strictly between 1 and n. Now, since a is a divisor, of n, since a divides n, there is a b such that n is equal to a times b. And since both a and n are positive, since a and are positive, so we know that b has to be positive. Hence, since b is an integer, hence b is greater than or equal to 1, because b is an integer. And now again, by comparison principle, again, by comparison property, we have b is less than or equal to n. Because b is also a divisor, this condition tells you b is also a divisor of n, and both b and n are positive, though you know that b is less than or equal to n. So we have b is greater than or equal to 1, less than or equal to n, okay? B is greater than or equal to 1, b is less than or equal to n, so you get b is between 1 and n. Now we want to show b is strictly between 1 and n. So if b is equal to 1, then by this condition, n is equal to a times b, then a would be equal to n. But this is a contradiction. Because we know that we already showed that a is between 1 and n, strictly between 1 and n. So A cannot be n, contradiction. On the other hand, if B is equal to n, by this property again, n is equal to A times B, then we have A is equal to 1. Again, a contradiction, because A is strictly greater than 1. So therefore, this 2 implies B is not equal to 1, and B is not equal to n. Now, because B is between 1 and n, but B is not equal to 1, B is not equal to n, therefore, we have B is strictly between 1 and n. Okay, so this lemma tells us an integer is composite if and only if you can find two numbers a and b both strictly between 1 and n, so that the product is equal to n. It's equal to. All right. So the next lemma is the basis for the fundamental theorem of arithmetic. So which tells you that for any integer greater than or equal to 2, there always exists a prime number that divides the integer. So if n is greater than or equal to 2, then there is a prime number p such that p divides n. So you have a prime factor, prime divisor. Okay, so this proof uses the basic property for natural numbers. So we'll construct a subset of the natural numbers, and then we'll show this set has to be empty. So we'll let S be the set of or natural numbers greater than or equal to 2, which has no prime divisor. Okay, so if we can show the set S is empty, then the lemma is proved. So we want to show that S is empty. If S is empty, which means every natural number greater than or equal to 2 has a prime factor, prime divisor. So we'll prove by contradiction. So if S is not empty, okay, recall the basic property for natural numbers. Any non-empty subset of the natural numbers has a minimum. Then S has a minimum. M. Okay, all right. So since M is a member of S, but if you look at the definition of S is a set of all natural numbers greater than or equal to 2, which has no prime divisor. So we have M is a so M has no prime divisor. But since M itself is a divisor of M, so M is not prime. So M is not prime. Okay, because M itself is a divisor of M, but M has no prime divisor, so M is not prime. So if M is not prime implies by definition M is composite. So M is composite, we just have a lemma. If M is composite, then there exists, so by previous lemma, there are A between 1 and n, and B between 1 and n, so that M is equal to A times B. Now, we want to use the minimality of M. Since M is the minimum of S, so, but A and B are less than M, so since M is the minimum of S, and A is less than M, so we know that A does not belong to S. So A is not a member of S. Again, by the definition of S, this tells you A must have a prime divisor. So by the definition of S, A has a prime divisor. P. But since A divides M and P divides A, so the transitivity property tells us P divides M by transitivity. But this is a contradiction since P is a prime divisor of M. Contradiction. Okay? Because M has no prime divisor, but you prove that P is a prime divisor of M. This tells you S must be empty. S is empty. This tells you there are no natural numbers greater than or equal to 2. which has no prime divisor. That means every natural number greater than or equal to 2 has a prime divisor. So any questions about this lemma? Okay, so so this is the one of the most important lemma for lambda theory, and the next theorem is also a very beautiful theorem. It's called the Euclid theorem. So this theorem tells us there are infinitely many prime numbers. There are infinitely many prime numbers. Again, this proof uses contradiction. So we assume there are finite many prime numbers, and then we will construct a number which is a new prime number. This would be a contradiction. Okay, so let's look at the proof. But you can see, actually, the constructive proof is always very difficult. In other words, if you want to directly construct an infinite sequence of prime numbers, that's always going to be very difficult. But the contradiction just tells you the existence of infinite many prime numbers, but doesn't tell you how to find them. Okay, so assume there are only finitely many prime numbers. Since there are finite many, we can denote them by P1, P2, up to some Pn, finite many. Now we'll let P be the product of those P numbers, prime numbers, Pn, and we add 1 to the product. So we'll show this P must be a prime numbers. So we'll show P is a prime number. Okay, so you can see here in this in the proof of the contradiction, we use another proof by contradiction, okay, to show P is a prime. If P is not a prime number, recall the lemma we just proved. Every composite number has a prime factor. So if P is composite, then P has a, so by our lemma, P has a prime divisor. Okay, so P has a prime divisor, but you should remember our big assumption here. We assume there are only finite many prime numbers, and all those prime numbers were listed as P1, P2, up to Pn. So the prime divisor of P must be one of those Pn's. So one of the PI's must be a divisor of P. Okay, we say, so just let pk divides P with, of course, this k is somewhere between 1 and n. So now what we can write is then you can write here, recall this condition, P is equal to the product plus 1, then P is equal to pk multiply, so the remaining P1, P2, pk minus 1 times pk plus 1, Pn plus 1. Okay, you just take out pk from the list and put it in the front. But then this is contradiction because this pk cannot be a divisor of P. This implies that pk does not divide P. But this is a contradiction because we just said that pk divides P, but the definition of P tells you that pk does not divide P. Contradiction. So this tells you, so P is a prime number. And on the other hand, this P is greater than or equal to any Pn. On the other hand, P is equal to P1 times P2, Pn plus 1. So this is greater than pk for any k between 1 and n. Okay, the reason is because pk is one of the component in the product, but all other factors are greater than or equal to 1. So you can see this product, this part is already bigger than pk, but you still add a 1 here. So P is greater than pk for any k between 1 and n. So this is a contradiction with our assumption, because our assumption said that P1 up to Pn are all the prime numbers, but you get a larger prime number. So this contradicts. With P1, P2, Pn is a complete list of primes. Okay. So you can see the proof of Euclid's theorem is very pretty. So you just assume there are finite many. You construct a new number which is bigger than those numbers, but then you can show this number must be a prime number. So in other words, the hypothesis is not true. There can be finite many prime numbers. So we have infinite many prime numbers. Okay. Okay, so the NOT theorem strengthens the theorem we just proved. We proved that a natural number is composite if and only if there exists A and B strictly between 1 and n, so that n is the product of A times B. But the next theorem tells you actually any composite number has a prime divisor which is less than or equal to the square root of n. So if n is a composite, then there exists a prime divisor P of n such that P is less than or equal to the square root of n. So you have a better control of this prime divisor. It's less than or equal to the square root. Okay, so let's look at the proof. So we will use the theorem proved earlier. Since n is composite, there are A between 1 and n, and B between 1 and n, so that n is equal to A times B. All right, so since n is a product of A and B, then at least one of the A and B's is less than or equal to n. Then either A less than or equal to root n, or B is less than or equal to root n. Because if both A and B are greater than or equal to root n, then the product would be greater than n. Well, since because if a is greater than square root of n, and b is greater than square root of n, then a times b would be greater than n. All right, so one of a or b would be less than or equal to square root of n. So we can just assume, since a and b has no order here, we may assume just a is less than or equal to square root of n. The case when b is less than or square root of n is the same. Now, since a is less than or equal to square root of n, and also a is greater than 1, then by the previous theorem, any number greater than 1 would have a prime factor. Then by previous theorem, a has a prime divisor p. Now, since both a and p are positive, hence we have p divides a, and p would be less than or equal to a. Now, since a divides n, and a is less than or equal to root n, so we know that p divides n by transitivity, and p less than or equal to root n. Okay, so now this tells you p is a prime divisor of n, which is less than or equal to root n. And the case b less than or equal to square root of n is similar. All right, so this theorem, this strengthening of the theorem is very useful, especially when you try to decide a given number, whether a given number is a prime or not. So here is the application. So this theorem tells us if you want to determine whether a given number is composite or prime, you just need to look at all the prime numbers which are less than or equal to square root of n, and check those whether those prime numbers are divisors of n or not. If no prime numbers less than or equal to square root of n divides n, then n has to be a prime number. Okay, so let's look at one example, then we're done. Okay, show that 97 is a prime number. All right, so we already know 97 is a prime number, but how to prove it? If we don't have the theorem in hand, you have to check from 2, 3, 5, 7, you check all the prime numbers which are less than or equal to 97. Less than 97 to see whether they divide 97 or not. So you can see there is a long list, okay, starting from 2 up to 96. There are many prime numbers, so you have to check a lot of divisions. But so that's not effective. Now, using the theorem we just proved, we have a simple way to prove it. Prove. So since square root of 97 is less than square root of 100, which is equal to 10. 10. We only need to check the prime numbers two, 3, 5, 7. Check if the prime numbers 2, 3, 5, 7. So all of those are less than 10. Are divisors of 97. Okay. So, but it's clear that now it is clear it is easy, a simple computation. Simple computations show that none of 2, 3, 5, 7 is a divisor of 97. Hence, by the theorem, by the previous theorem, '97 is prime. Okay, so you can see this theorem is very useful to determine whether a given number is a prime number, because by taking the square root, you reduce the number to a very small quantity. Then it's much easier to justify whether those prime numbers are divisors of the given number. So any questions about this example? All right. So if you don't have questions, so we'll stop it here today, and I'll see you next week. Bye-bye.